Today's session is about Introduction to Nonlinear Systems. A nonlinear system is one in which there is no linear relation between the input and the output. That means there is no linear relation between the cause and the effect. From the control perspective, a linear control is a mature subject with a variety of powerful methods and a long history of successful industrial applications. But we can see that almost all systems in nature are inherently nonlinear. The knowledge of linear control proved insufficient to study the behavior of nonlinear systems. This led to the development of special tools for nonlinear control systems. The two streams of nonlinear control are design of nonlinear control systems and analysis of nonlinear control systems. By analysis, we assume that a nonlinear control system is already designed and we need to determine the system behavior. By design, what we mean is we are given a nonlinear plan to be controlled and certain specifications of the closed loop behavior are also given. What we need is to construct a controller so that the closed loop system meets the required specification. But in practice, we can see that the issues of analysis and design are closely related because design and analysis are iteratively involved in design. Here we discuss why researchers show keen interest in nonlinear control. 4 points are to be discussed. The first one, improvement of existing control systems. One method of studying nonlinear system is by reducing the nonlinear system to a linear system. The assumption made here is the linear model is valid in a small operating region. For example, if you consider the relation y equal to 3x square, we can see that in a small operating region, this can be treated as a linear relation. But if the operating region is large, it is no more a linear relation. Hence, when the operating range is large, the linear control fails and we require nonlinear controllers. Coming to the second point, the analysis of hard nonlinearities. In linearizing a nonlinear model, another assumption is the system model is linearizable. But there are certain nonlinearities which cannot be linearized. For example, if you consider a relation between the input and the output, that is x and y, as shown here, we can see that for a certain range of x, y is linear. But beyond a certain value of x, y is a constant. This is an example for a hard nonlinearity. This is called saturation nonlinearity. So in systems with hard nonlinearities, we need to use nonlinear control techniques. So coming to the third point, dealing with model uncertainties. For linear control technique, it is usually necessary to know the planned model. But if there are uncertainties in the planned model, it will affect the controller designed for the uncertain model. Let us assume that we are designing a controller for a robotic arm. Assume the robot accidentally picks a heavy object. If this model uncertainty is not included in the planned model, then a change in the inertial parameter will definitely affect the linear controller. The linear controller designed for this system might fall out of place in such a sudden change in the model parameter. But this issue can be easily tackled by a nonlinear controller. Finally, for a nonlinear system, there are well-developed simple and effective nonlinear controllers. Hence, it is better to use nonlinear controllers for nonlinear systems. So here we discuss the characteristics of linear systems. The first one, linear systems satisfy the principle of superposition and homogeneity. For example, if you have a system whose input is x1 and corresponding output is y1, and if you have another input x2 and the corresponding output as y2, then if you give the input as x1 plus x2, the corresponding output would be y1 plus y2. This is principle of superposition. This holds good for linear systems. Then coming to homogeneity. If you have an input x1 and corresponding output as y1, then if you increase the input by k units. Say kx1 is the input. Then the corresponding output would be ky1. That means a scaled version of the input results in scaled version of the output. Coming to the second one, that is asymptotic stability implies bibostability. This was extensively discussed in the stability videos. Asymptotic stability is otherwise called internal stability, which is related to eigenvalues. So, asymptotic stability implies bibostability. The third one says a sinusoidal input results in a sinusoidal output of the same frequency. For example, if you have a linear system and if I give an input of sine wave with say 50 Hz, then the output will also be a sine wave of 50 Hz, but the amplitude can change. Also there can be a phase shift. The fourth point says unique equilibrium point. Let us assume a linear system defined by x dot equal to ax. If capital A matrix is a non-singular matrix, which means determinant of A is not equal to 0. In that case, we can say that the system has a unique equilibrium point. An equilibrium point is a point where the system states remain unchanged. So, if you have the system model like this, when you say that the system states remain unchanged, it says there is no change in the state. So, we can write x dot equal to 0. Let us assume we have a state model given by x dot equal to 0, 1, minus 2, minus 3 into x. Since we are considering only the stability of the equilibrium point related to the initial condition, let us assume an unforced system. So, in this case, we can write x1 dot equal to x2 and x2 dot equal to minus 2x1 minus 3x2. So, at equilibrium point, there is no change in the state, which means x1 dot equal to 0 and x2 dot equal to 0 as per this condition. So, this results in x2 equal to 0 and thereby x1 equal to 0. This is a unique solution. This says that the solution for x dot equal to 0 is x1 equal to 0 and x2 equal to 0. Thus, for linear systems, if capital A matrix is non-singular, we have a unique equilibrium point. Now coming to the fifth point, local stability implies global stability. This is again something related to asymptotic stability or the stability that is related to the eigenvalues. Let us assume that we have a system model represented by x dot equal to ax. Let us assume that x of 0 represents the initial state. Assume that this x of 0 is very close to the equilibrium point given by xe. If the system is stable, x of 0 will gradually move towards the equilibrium point as time t tends to infinity. And if you consider another initial point x of 0 which is away from x of e, then again we can see that it gradually moves towards the equilibrium point. This shows that stability is not a local phenomena, but it is a global phenomena. That is, irrespective of x of 0, the system is stable. This shows that local stability implies global stability. Hence, if the system is locally stable, then we can ensure that it is globally stable. The last point says, for linear systems, a general solution can be obtained for the system description equation. This means that we can have a closed form solution for linear system description equations. So, here we discuss the characteristics of nonlinear systems. The first one is multiple equilibrium points. We have seen what an equilibrium point is. An equilibrium point is defined as x dot is equal to 0. It shows at equilibrium points the states remain unchanged. So if you consider a relation x dot is equal to minus x plus x square, then at equilibrium point this equation becomes 0. So this results in minus 1 plus x into x equal to 0. This implies x equal to 0 or x equal to 1. This shows that there are two equilibrium points. As far as nonlinear systems are concerned, the equilibrium points can be stable or unstable. Consider the case for x equal to 0 being a stable equilibrium point. It means that if an initial state x of 0 is considered near x equal to 0, then this state gradually moves to x equal to 0 as time passes. Similarly, if you assume that x equal to 1 is another equilibrium point, and if you consider an initial state x0 very close to x equal to 1, then we can say that if x equal to 1 is an unstable equilibrium point, then this initial state will take the system away from x equal to 1. So, as far as nonlinear systems are concerned, we can have stable as well as unstable equilibrium points. So, the stability of the nonlinear system all depends on the initial state, whether it is close to an equilibrium point which is stable or unstable. Now coming to jump resonance. Let us consider a spring mass damper system whose system dynamics is represented by m into d square x by dt square plus b into dx by dt plus kx equal to the input. Here we can see that this is a linear spring. In that case, the frequency response of this system would be like this, where this is the frequency and this is amplitude. Let us consider a spring mass damper system which is given by the relation m into d square x by dt square plus b into dx by dt plus k 1x plus k2x cube equal to input. In this case, we can see that this relation is a non-linear one. So, if K2 is greater than 0, we call it a hard spring, and if K2 is less than 0, we call it a soft spring. A spring is classified as a non-linear hard spring when the restoring force increases faster than that given by Hooke's law. So, the frequency response of this system with a non-linear spring characteristics would be something like this. So, in this case, we can see that as frequency increases, the amplitude gradually increases. Once it reaches this point, you can see that it gradually falls to this value from B to C. And once the frequency is increased from that region, then the amplitude changes like this one. And similarly, when the frequency is decreased, we can see that it takes a path like this one, and once it reaches this point, it moves back to say F. And then if the frequency is decreased, it moves from this point. So, this shows that as the frequency increases, there is a hysteresis change with an unusual jump in the frequency response. So, this is something like a hysteresis change. This phenomena is called jump resonance. It is shown by nonlinear systems. Next we have the third feature of nonlinear systems, that is frequency entrainment. When excited by a sinusoidal input of constant frequency, the output frequency at some point exactly matches with the input frequency, and this continues thereafter as the amplitude is increased from low values. This phenomena, which results in a synchronization of matching of the output frequency with the input frequency, is called frequency entrainment or synchronization. Next is finite escape time. As far as linear systems are concerned, if a state has to go to infinity, it will take infinite time to reach infinity. And in the case of nonlinear systems, it takes only finite time to reach infinity. And this is called finite escape time. Next is limit cycle. As far as linear systems are concerned, if there are poles on the imaginary axis, then the response of the linear system will be purely oscillatory. In the case of nonlinear systems, we can see that there are sustained oscillations of fixed frequency exhibited by them at certain cases. These sustained oscillations of fixed frequency and amplitude are called limit cycles. In the figure shown here, there are two different types of limit cycles. One is a stable limit cycle and the other is an unstable limit cycle. In the figures, we can see that x1 and x2 are the state variables. They are called phase variables because they are state variables in which output and its derivative are taken as the state variables. In the case of a stable limit cycle, we can see that the nearby trajectories get into the limit cycle as t tends to infinity. Here we can see that the neighborhood trajectories move into the limit cycle as t tends to infinity in the case of a stable limit cycle. Whereas in the case of an unstable limit cycle, it is said that the nearby trajectories move into the limit cycle at t tends to minus infinity, which means the system trajectories were on the limit cycle at t equal to minus infinity, and now it has left the limit cycles. Hence they are called unstable limit cycles. The next feature of a nonlinear system is harmonics in output. Suppose that a nonlinear system is excited by a sinusoidal signal of fixed frequency. Then in the output we can see that there are several harmonics in addition to the fundamental frequency. This can be checked by taking the Fourier series of the output signal. The next feature says nonlinear systems do not obey the principle of superposition and homogeneity. The last one is local stability does not imply global stability. As far as nonlinear systems are concerned, we cannot form closed form general solutions. The stability of the nonlinear systems is highly dependent on initial conditions. In one of the previous slides, we have seen the multiple equilibrium points of nonlinear systems, wherein we had seen equilibrium points at x equal to 0 and x is equal to 1. There we had seen that when the initial conditions were closer to x is equal to 0, the response moved towards x is equal to 0 as time t tends to infinity, and when the initial condition is close to x is equal to 1, then the response moves away from the x is equal to 1 equilibrium point. This shows that the stability of the nonlinear system depends much on the initial condition. This says local stability does not imply global stability. The analysis techniques of nonlinear systems can be broadly classified into four. One, linearization technique. The second, phase plane analysis. Third, describing function analysis. And fourth, Lyapunov stability analysis. The linearization technique is a very old method of analyzing nonlinear systems. Linearization is basically an approximation of the system in the neighborhood of an operating point in the case of a nonlinear system. It shows a local behavior in the vicinity of that operating point. Hence, it cannot predict the global behavior of the system. that is, the behavior away from the given operating point in the entire state space. But we can see that linearization is useful information. In some cases, linearized model has to be modified when the operating point moves from one point to another. Next we have the phase plane analysis. This is used totally for second order systems. We have seen that a phase plane is nothing but a plane formed with state variables x1 and x2. Since we are confined to a second order system, we have only two state variables x1 and x2. Here, one of the state variable will be the output y and the other will be y dot, its derivative. In such cases, the state variables are called phase variables. And a plane which is formed of x1 and x2 will be called as phase plane. So the phase plane will basically show y and y dot variation. This is used for the study of the nature of the phase trajectories, that is how these state variables move near the equilibrium point. The periodic oscillations called limit cycles can also be identified using this approach. A study of the stability of the systems can also be performed using this method. Next is describing function analysis. It is a frequency response analysis. As far as nonlinear systems are concerned, we cannot find the transfer function. So this describing function analysis is also called harmonic linearization. We will see more details of describing function analysis in the upcoming videos. This is used for the study of existence of limit cycles and its properties. We can also study the stability analysis of nonlinear systems using describing function analysis. The last one is the Lyapunov stability analysis. The analytical solution of a nonlinear system description is rarely possible. We have seen that closed form solutions cannot be obtained for nonlinear systems. So if a numerical solution is attempted, the question of stability behavior cannot be fully answered because it depends upon the initial conditions. So Russian mathematician A.M. Lyapunov introduced and formalized a method by which one can conclude about stability without solving the system description equation. Because of this intuitiveness and physical insight, this method is widely accepted among control engineers. Thank you.